So, welcome to the lecture on 2 degree of freedom systems. So far we have discussed the undamped cases, undamped free vibration case, the damped free vibration case. We have discussed the coupling of the two modes. We have discussed mode shapes and the natural frequencies. Now we are going to discuss the forced vibration of a 2 degree of freedom system. So, what is a forced vibration? So, in compared to the free vibration, as free vibration we disturb the system and we release the system. So, the system starts vibrating with its own natural frequency when it is undamped. When it is damped, it starts with the damped natural frequency. However, when we have a forced vibration and we apply some harmonic load, here we will talk the forced vibration with harmonic load. So, harmonic load is a load that varies like sinusoidal or cosine manner. So, when our system is subjected to a harmonic load, so the response of the system contains two parts, that is transient part and the steady state part. So, the transient part, that due to the effect of the damping, it will die out very soon. However, the steady state part, that is due to the external loads, that will remain there due to the till the load is there. Okay. And we know that in case of steady state vibration, the steady state response, the vibrations usually have the vibration of the system. So, the system vibrate with the same frequency as the forcing frequency. So, if I have a system that has some natural frequency 5 hertz, but I have applied a load that is 15 hertz. So, the system, so steady state response, the vibration will contain the 15 hertz frequency. When the forcing frequency is equal to the natural frequency of the system, like if I have my system has 5 hertz frequency, natural frequency, and I apply a load, harmonic load that has also the frequency of 5 hertz, then that is called the resonance condition, and in that case the amplitude of vibrations are very high. Okay, so these all things we have already discussed, and here I just wanted to recall because I am going to discuss the forced vibration of 2 degree of freedom system. So, let us take a system. So, this is our system 2 degree of freedom system. So, we have two masses M1 and M2 and two springs K1, K2 and K3, and the force, harmonic force is applied on the first mass, and that is F0 sin omega t. So, F0 is the amplitude of the force and omega is the frequency of that force. So, let us study this system. Okay, so we have this system M1, M2 and K1, K2, K3. Here we have not, for simplicity, we have not considered the damping. Now this we have applied the force on F0 sin omega t on mass m1. So to understand, to study the vibration response of this system, we have to write the equations of motion and then solve it. So equations of motion we need to write, and so we make the free body diagram. So let's have this m1 mass and we make the free body diagram. So if at that instant of time it is x1 here and its acceleration is directed towards the same direction of x1, so we are going to pull this spring. So this spring will apply a force k1 times x1. However, this spring, if we assume x2 is greater than x1, so we will, this spring will also apply a force here k2 x2 minus x1. So net it will pull this mass. However, there is one force F0 sin omega t also, that is external force acting on the system. For the mass m2, we have this force in this direction due to the spring k2, and because it is compressing this spring, so this spring will apply a force in this direction, that is k3 times x2. Okay. So we have to write the equations. So we can write for the first mass m1. So m1 x1 double dot equal to summation of the forces, and so forces are minus k1 x1 plus k2 x2 minus x1 plus f0 sin omega t. So we can rewrite this equation m1 x1 double dot plus k1 x1 plus k2 x1 minus k2 x2 equal to f0 sin omega t. So we can write m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 equal to f0 sin omega t. So this is equation number 1. Now we have to write the equation of motion for the second mass. So we write m2 x2 double dot equal to, so we have this is the direction of x2 double dot. So we have minus k3 x2 minus x1 minus k3 x2. So we can write m2 x2 double dot plus, so it is k3 x2 sorry, this is I think k2, so plus k2 plus k3 x2 minus k2 x1 equal to 0. This is equation number 2. Now we assume the steady state condition. We are going to be interested in the steady state condition. So, steady state condition, as I said that the system will vibrate because system is subjected to some external force, external harmonic force. So, the system will vibrate with the same frequency as the forcing frequency. Okay. So, we can assume the solution. So, x1 equal to x1 sine omega t and x2 equal to x2 sine omega t, where capital X1 and capital X2 they are the amplitude of the response. So, now we put these values in this equation. So, here we have x1 double dot equal to minus omega square x1 sine omega t, and here x2 double dot equal to minus omega square x2 sine omega t. So, we can put in this equation. So, m1 minus omega square x1 plus k1 plus k2 into x1 minus k2 into x2, and this is sine omega t equal to f0 sine omega t. So, we can leave the case of sine omega t equal to 0. So, we will have m1 omega square plus k1 plus k2 x1 minus k2 x2 equal to f0 sine omega t. So, this is equation number 3. Now, the second equation, if we put these solutions, so m2, so minus omega square m2 x2 plus k2 plus k3 x2 minus k2 x1 sine omega t equal to 0. So, here we have minus sorry, here this is like this. So, here we can have minus m2 omega square plus k2 plus k3 x2 minus k2 x1 equal to 0. So, from here we can find x2 by x1. So, we can write x2 equal to k2 by minus m2 omega square plus k2 plus k3 into x1. Okay, so this equation number 4. Now we put the value of x2 in this equation, because we have to solve these equations. So minus m1 omega square plus k1 plus k2 x1 minus k2 square. So if we put x2, so it is k2 square upon minus m2 omega square plus k2 plus k3 into x1. We put here x1 equal to f0. So we solve this equation. So we can multiply here. So minus m1 omega square plus k1 plus k2 and minus m2 omega square plus k2 plus k3 minus k2 square equal to f0 into minus m2 omega square plus k2 plus k3 by x1. So x1, so we can multiply here. So m1, so this is m1 m2 omega power 4 minus m1 k2 plus k3 omega square minus m2 k1 plus k2 omega square plus k1 plus k2 into k2 plus k3. Minus k2 square, that is equal to this same term. So we can rewrite this. So we will have m1 m2 omega power 4 minus m1 k2 plus k3 plus m2 k1 plus k2 omega square plus this is k1 k2 plus k1 k3 plus k2 square plus k2 k3 minus k2 square, and k2 square will cancel out, and that is equal to f0 by x1 into minus m2 omega square plus k2 plus k3. So here we can write x1 equal to f0 minus m2 omega square. So we can write like k2 plus k3 minus m2 omega square upon m1 m2 omega 4 minus m1 k2 plus k3 plus m2 k1 plus k2 omega square plus K1 K2 plus K1 K3 plus K2 K3. So this is the denominator term, and so we can get also K2 x2. So x2 is equal to, so x2 equal to K2 x1 by this term. So x1 by this term we put here, so it is K2 f0 by so m1 m2 omega power 4 minus m1 K2 plus K3 plus m2 K1 plus K2 omega square plus K1 K2 plus K1 K3 plus K2 K3. Okay, so we have obtained the amplitude of x2 and x1. So let me rewrite here because I want to discuss some concept. So K2 plus K3 minus m2 omega square upon m1 m2 omega 4 minus m1 K2 plus K3 plus m2 K1 plus K2 omega square plus K1 K2 plus K1 K3 plus K2 K3. Okay. Okay, so we have these response amplitudes of x1 and x2. So what we see that we have this response of x1 also, I mean there is, if force is 0, they are x1 and x2, they are 0. This denominator term is nothing but this is the frequency equation, and so if we solve that equation it will give the natural frequency of the system. One more thing we can notice that x1 is 0 when this term is 0, that is K2 plus K3 minus m2 omega square is 0. So it means that m2 omega square equal to K2 plus K3, and so omega equal to K2 plus K3 by m2 under root. So what it implies that if the excitation frequency omega is equal to under root of the K2 plus K3 by m2, the amplitude of x1 is 0. So this mass m1 will be at rest. So it means that if we select, we can select the value of K2, K3 and m2. So if we can select this system such that K2 plus K3 by m2 under root equal to omega, then this mass will come at rest. So this gives the principle of vibration absorber that are used for bringing the main system to rest. If some force is coming to the main system, we can select an auxiliary system such that the following this relation, so that the vibration of the main system comes to 0 and that vibration is transmitted to the vibration of the mass m2, and here we see that the vibration of x2 is not 0. So vibration of mass is m2 is not 0, but vibration of m1 is 0 here. So this gives the principle of vibration, dynamic vibration absorber, and that we will discuss in detail in the next class. So we saw that in case of forced vibration, the system vibrates with the same frequency as the forcing frequency the steady state response contains, and that frequency. Moreover, in case of 2 degree of freedom system, we can select the parameters of the springs and secondary mass in such a way that we can bring the first mass to rest for any excitation frequency omega, and this will give the theory for the design of the vibration absorber. So that we will discuss in detail in the next classes. So I stop here and I thank you for attending the lecture, and see you in the next lecture.